Alright, here's another video explaining some things in Physics C to review. In this case, we're going to be looking at force of gravity inside a sphere and outside of a sphere. So let's say we have a planet here, and it's got a density of some sort. In this case, we don't know. And we'll look at two different cases here where we have a uniform density and a non-uniform density. Assuming a geometrical shape here that's symmetrical outside the sphere, no matter what happens, it's going to be equal to force gravity equals g m1 m2 over r squared. Okay, of course, if I'm located out here, maybe I'm the m1 here, and m2 would be the mass of this whole sphere. And of course, radius, we're going to come from the center, because all of the mass will look like it comes from its center. And we're out to here at some location. Okay, and we can easily calculate what the force of gravity outside the sphere should be. Now, inside the sphere, so let's say I'm located at about a radius right here. I want to know what's the gravity force there. Well, inside the sphere, we do have to consider the differential dm, which equals density rho times some kind of dv here. Now, dm has a variety of ways of looking at it, depending if it's uniform or non-uniform. So let's just look at the general equation for that. So dm could equal some kind of density factor based on the radius. So this is density sub r, meaning a function of a radius. And then how are we going to do this dv? Well, dv would then be surface area of a sphere, which is 4 pi r squared. Okay, times some dr, some differential of r. So imagine the surface area of this sphere location here. It looks like a circle, but think of it as a sphere. And then we go a little bit farther out, a differential of r, and then we have another sphere there. So that's kind of what we're talking about. So dm is going to be equal to some density factor times this 4 pi r squared dr. Okay. Let's look at uniform density, though. Let's say we're inside the circle here. So this sphere has a radius, and let's say the total radius is equal to some value a, and then r is going to represent, the location from the center where we are inside the sphere. So of course, if we're located at the surface, then our radius would be r, and then we've got the whole mass of the planet here. Okay, so if we have a uniform density, then we're going to say the mass enclosed, or mass inside all of this small sphere inside. So the mass over 4/3 pi r cubed must equal the mass of the whole planet divided by 4/3 pi a squared, because this is uniform density. So the volume density of this has to equal the volume density of the whole thing. So what's the mass enclosed then equal to then? Well, all I got to do then is solve for this expression here. My 4/3 pi's are going to cancel out, and I'm left with the mass enclosed then is going to equal the whole mass of the planet times r cubed over a cubed. Okay, r cubed is going to be the radius where I'm located, and of course a cubed is the radius of the whole planet. So basically all I'm finding here then is kind of like the mass fraction of the whole planet. How much of the whole planet am I here? Okay, and then the force gravity for that, we're just going to plug that into where we have g m1 m2 over r squared. So let's say I'm located right here. What would be the force of gravity acting on me? Would be g m1, and then of course m2 is going to be what I just found here for the planet, being the inside that radius mass that I'm looking at. Okay, so that would be m r cubed, okay, over a cubed. And what's my end result? G m1, which would be my mass, multiplied by m r over a squared. So that would be equal to the force of gravity acting on me at this particular location. Now, of course, what if I don't have a uniform density here? Suppose density is equal to some factor b, okay, times the radius. Okay, now we have to actually integrate. Okay, so mass is equal to the integral of dm. In this case, would be equal to the integral of 0 to r, okay, of our radius-based density function multiplied by 4 pi r squared dr. Now, of course, we don't have a multivariable situation here because our density is in terms of r. So what would that look like? So m would be 0 to r, okay, times b times 4 pi r cubed dr. Now where do we get that from? Well, all I've done is I've substituted in for this expression here, b times r. And that leads to b 4 pi r cubed dr. Okay? And what's that going to equal? Well, the integral of r cubed, of course, is 1/4 r to the 4th. So our 4's are going to cross off. So mass then is equal to pi b r to the 4th. Now, of course, I can plug that in where I see force gravity. Force gravity then is going to be g m1 times pi b r to the 4th over r squared. And then in result is going to be g m1 times pi b r squared. Okay, and that's going to be equal to the force, okay, that's inside, okay, the sphere. And that's, you know, a pretty reasonable, you know, way of looking at it when you have a non-uniform density. And of course, you're going to need to have, you know, some way of figuring out what b value is, or it's going to be given to you of some kind of function. Okay, and that's our video for this lesson.